All right, so we're going to do some logs and exponential revision. And so for the first one, it says write it in its simplest form. So this is all indice laws. So I would say the first thing you would do, just like with anything, let's try and remove the brackets. So the first thing you have to remember that the power on the outside has to be times by all the powers on the inside. So what we're going to have is negative 3 to the power of 3 times a. Now what would be 3 times n? It'd be 3n times b. Now you're going to times all of that by 3. So be careful with that. And then this 4, if we look at this 2, this is only multiplying what's inside, okay? So the 4 is on the outside of the brackets. So we've really got, you might say 4 times a to the power of 2 and times b, and it'll be 2 times that power there. All right, I'm not trying to rush it too much because if you step it out, you'll be able to spot your mistakes, you know, because you can follow step by step, and it'll meet neat. So I'm going to get rid of the bottom brackets. So it'll be 2 to the power of 6. A, now it'll be 6 times that power, and B, 3 times 6, which would be 18. So I'm going to keep tidying up now. Now, what's negative 3 to the power of 3? 3 times 3 times 3 would be? 27. And because it'll still be negative, won't it? Yeah? So I'm going to write negative 27. Would that be true? Because negative 3 times negative 3 gives a positive, but then when you times it by negative 3, doesn't it give another negative? Are you hearing me? So negative 3 times negative 3 times negative 3. These two made it a positive, yeah? And then you go one more time, makes it the negative 27. All right? Okay? And then we've got a 3 to the power of n. Then I'm going to multiply this bracket out. So I've actually got 6n minus 6 times 4 times a to the power of 2 times b. And it's going to be 2 minus 2n. Okay? All over 2 to the power of 6. A times a, 6n plus 12 times b, 18. I'm getting a little bit kooky, so I'm changing pen colour. All right, so you might do different thing, but I reckon the best way is to go across that way and do the things. So when we have powers, the bases are the same, but the powers are different, and we're multiplying, what do? So say for this guy and this guy, they're the same base. A is the same base. What do I do with their powers if I'm multiplying? You add them together. Are you happy with that? Yes? So I'm not doing anything with the 27 at the moment. Though I might move that 4 because I'll do that in a minute. So then I've got I've got 3n plus 2, haven't I? Yes? So I can't really add, I can't really add them, so I'm going to leave that as a 3n plus 2 times b. Now I've got 6n plus and minus 2n, so that would give me 4n, and I've got a negative 6 plus a 2, which would give negative 4 all over. Now can I add it? I'm going to leave 2 to the power of 6 times a, 6n plus 12 times b, 18. Yeah? So you can keep going. So if you did negative 27, or maybe we will change that. We'll leave that 27. And now what I'm going to do is I'm going to bring these powers down here, and I'm going to bring them up the top because we've got the same bases up here, haven't we? And what I'm actually going to do is change this 4 here to what could 4 be with a base of 2? 2 squared, yeah? So what do we do when we divide? We minus, good. So I'm going to say it's 2 minus 6, see, because I'm doing those ones, yeah? And then I'm going to do it's 3n plus 2 minus 6n plus 12, isn't it? Yeah? And then I've got times, so there's all time. The b, up the top I've got 4n minus 4, and I'm going to minus 18. Okay? Sorry, we're going to move this up. See how it does get a little messy, doesn't it? So I'm just changing pens so you guys don't get lost. So at the moment, I've got negative 27 times 2 to the negative 4 times. Now, it would be 3n minus 6n, so that would be negative 3n. And then you've got 2 minus 12, so that would be negative 10. Yep. Times b, what would be 4n minus 22. Yeah? So then you can, if you like, you could just put them down the bottom. If the powers are negative, we could put that down the bottom. Leave the 27, so, I don't know, 27 times, we're going to leave it be 4n minus 22. And we might put the 2 down there, 2 to the power of 4. And I'll change these ones to 3n plus 10. Okay, so you could leave it like that. That's so simple enough. Change the 2 to the 4, that's all right. But can you see, it can take a little while. To me, that's the simplest. Negative 27 divided by 8 is not going to work. I mean, oh, what's that? I could have that, what's 2 to the power of 4? 16, isn't it? Yeah? Okay. So, you can leave it like that. All right, cool. Let's go to the next one. Okay, now for this one, solve for x in this. Now, if you look at this one, you can see that 4x is there, and see how this one, you could actually, couldn't I rewrite that as 4 power x like that? Would that give me the same, wouldn't it? Yes? Can you see that? So when you see one of these, you should hopefully see this is actually a quadratic equation that you can do. Because if I go like this and I say let 4 to the power of x equal, I'm just going to let it equal any letter. So I might say h this time. Okay? So what I've actually got is h squared minus 20h plus 64 equals 0. Can you see now that this is a quadratic? Yes? Quadratic. So the way we solve a quadratic is we let the left-hand side, we make it all on one side and let it equal 0. That's already done for us. And then we might look for a pattern. It doesn't look like, this is 8 squared, isn't it? But is this 2 times 8 in there? No. So it's not one of the patterns. That's not 2 times. So what would we do if we don't have that? We would try the cross method, yeah? So I'm going to break it up, h and h. Now I need something that multiplies to give 64, positive 64. But if they add, give negative 20. So I've had to think about it. And maybe what if I said negative 16 times negative 4? Would that work? So negative 16 times 4, does that give positive 64? Yeah, it does. So, and then, remember we checked. So if I multiply that, that would be negative 4h. Multiply this guy, that would be negative 16h. Do they add to give this guy? Yes? They add and give that. So I know I've got the right combination. So these will become my brackets. Okay, so I've got h minus 16 and h minus 4 equals 0. And then what do? Remember the null factor law? You say you let each factor equal 0. And then you know h equals 16 or h equals 4. But we don't want to know what h is. We said that h was 4x. Yeah? To the power of x. So 4 to the power of x equals 4. Now how could I write 16? It could be written as 4 squared. And that could be 4 to the power of 1 So therefore, x equals 2 or x can equal 1. All right? That's it. And you did a couple of them to begin with. All right, let's move to the next one. Here we go. So 5, we've got 5 times log 3 to the base of 3, 8 minus 2, blah, blah, blah. I don't want to have this here because that's going to stop me from doing my other log laws. So I want to move that into, so it's just log. So what happens when I move that? I can make it a power here, can't I? Yes? So I'm going to write that as log 3, 8 to the power of 5 minus 2 log 3, would help if I take it away, yeah? Log 3, 16 to the power of 2. Okay. Now, what's the rule when you minus logs? Logs of the same base there. Divide. Awesome. So I can say it's equal to log 3, 8 to the power of 5 over 16 to the power of 2. Now, we need to deal with these numbers, and these numbers are a little bit big if I was trying to just work that out. But I can see, and I know, because when I see 8, I often see 8 as 2 to the power of 3. Is that not right? Yeah? And I see 16 as 2 to the power of 4. Is that cool? Are you happy with that? I'm just changing that number. Now, you know how to deal with that. If you have a powers and a brackets, what do? Times it out. Okay, so I've got 2 to the power of 15, 3 times 5, yeah? Over 2 to the power of 8. And what do you do when you are dividing indices? So you've got 2 to the power of 15 divided by 2 to the power of 8 would be? Yeah, good. 15 minus 8, which would be 2 to the power of 7. Okay, so I can say that's the same as 2 to the power of 7. Okay, and what's 2 to the power of 7? Log 3, 32. Yeah? Oh, no, it's not. What am I doing? Come on. What is it? I'll quickly, this is what I would be doing. All right, 2 to the power of 4 we said was 16. 5 must be 32. 6 must be 64. And 7 must be 128. All right, cool. So log 3, 128. Okay. Now, that's not a power of 3 of any sort, yeah? You can't change that. So I would say that's the simplest you can get it. That would be your answer right there. Yeah? Okay, because remember the other way we would be going, we would say if we had log 3, 128, and we were trying to work out what it is, remember we say let equal x, and then we say 3 to the power of x equals 128. Is 3, a base of 3 to something give 128? No. So you wouldn't worry. So you know, not that, it's this. Okay? All right. Let's move on. These ones. So let's practice. Everyone should be watching these because I know you don't like them, but this is what you'll get. And you can get them on a known calc. All right. So for the graph of y equals 3 to the power of 2x minus 1. Okay, let's have a little think. This here, that 2 there, it just gives a dilation. Okay? So when you just have to sketch it by itself, you're never going to be able to show a dilation. It doesn't really matter, okay, when you're just sketching it. But, so you can see here, what I always do is I sketch the basic graph. So a basic exponential looks like this, yeah, where it asymptotes on, can you see that it asymptotes on y equals 0, this line along here. Isn't that true? It doesn't quite touch it. So if you have a look, what is this going to do? This is going to drop the graph down 1, isn't it? Mm-hmm. So if it drop down 1, what you're going to see is your asymptote, sorry, I'm just going to get the ruler out, drops down to -1, yeah? Because it was at 0. So now your asymptote is at y equals -1. All right, so I'm going to say you're not really going to see the dilation. Now, if the basic graph has an intercept at 1 and you've dropped it down 1, where's it going to intercept here? At what? 0, good. So you're going to go like that. All right, mine's pretty bad, but anyway. Okay, so if we were answering their question, where's the asymptote at y equals -1? What's the y-intercept? You can also do that properly. You can go y-intercept, isn't that when x equals 0? So I've got y equals 3 times 2 to the power of 0 minus 1. What's anything to the power of 0? 1 minus 1 equals 0. That's what we had, isn't it? So that's good. Now, the domain, let me go through the domain. So the domain is what values x can be. If you have a look here, looking at the blue line, doesn't x, I've got an x value for there. It goes on forever. So what's that in maths? Real field, excellent. So domain equals, you can just say real field. All right. Now, if I look at the range is what the y can be. So where do I start? It starts being y about here and goes up there. It doesn't go past this line, does it? So I'm going to say that the range, the rule's there. The smallest number it can be is not quite -1. Would you agree? Yeah? And then it can be anything bigger than that. So I'm going to say goes on for infinity above that. And infinity has to have a curly bracket. Yeah? So you can write it like that. Alright, so that's probably the easiest way to do it. Alright, so not too hard. You don't have to have that grey line there. Yeah? But I just like to draw a basic one and then I move it around and then rub it out. Yeah? Just to show what you're doing. Alright, next one. So, if you remember, let's have a think about this now. So this is the basic one over here. So I've just drawn a normal exponential. We now have a negative in the x there. Where does that's going to cause a reflection? Wherein? Reflection in the y-axis. Good. So if you're going to reflect this, it's like you're saying this is the mirror. If that's the mirror, then it'll look like this, won't it? Yeah? Yes. Okay, so I've got that bit. Now, what about this plus 3? That is going to move it up 3. So where was the asymptote at the moment? The asymptote for the original one was at y equals 0. Now you're going to go up 3. Like that? Yeah? And say y equals 3. So I'm going to... Sorry, rub that guy out. Moving him up now. He's going to look that shape, but he's going to go up there like... Oh my God, I'm getting worse. But he's going to look like that. Okay. So, originally, we had that intercept at 1. So, what's a quick way to know? If it's moved up 3, what's this intercept? 4. Let's go and check that anyway. Y-intercept is when x equals 0. I'm going to put x equals 0 into my formula. So y equals, anything to the power of 0 is 1 plus 3. Y equals 4. Awesome, that's what we got. Now let's have a look. Alright, so we're looking at the domain. The domain is what it can be. So we're looking at the blue line. Does x be everything? Yeah? See? Yep. So, domain equals real field. Awesome. And then if we look at the range is what y can be. Looks like it can only be from there up. So, yeah? So what are we going to say? Curved bracket. 3. Infinity. Okay? No worries. Sure sharp, it's on video, guys. Alright, now, we are doing log graphs. So, if you remember, here's the basic log graph over here. So the log is actually, remember when I said this? If you have an exponential, oh God, that's getting worse. But a log graph is a reflection in that one, remember? So we see, that's where we're seeing it asymptote like that, okay? Sorry, really bad there. Alright, so just to explain, we've got the basic log graph. Okay, now we're going to look at the little things that happen here. Now, first of all, we know there's some movement happening, but we don't normally like to see it written like that because we like to see what's been added or subtracted from x. So really, what we should do is factorize this guy first. So say I'm still going to have 2 log 2. What I'm going to do is I want x by itself. So if I take 2 out, I'd be left with x, but you also took 2 out of 3. Can you see like that? Yeah? So really what that 2-bit here is a dilation factor. Along with that, that's another dilation. Yeah? Okay, so if we, remember I said you can't really see the dilations unless you've got another graph to compare with. And we don't have to put it. We're just going to put the one they're asking. I've just drawn that grey one in to help you. So if we don't have that, so this was our basic one. What was the basic one's asymptoting on? It doesn't quite go past, would you agree if I say x equals 0, this line? Yeah? Doesn't go past that line. So when I've got this up here, this plus 3 over 2, doesn't that move the graph to the left by negative? So now I have this, I've got this asymptote over here, oops, at x equals negative 3 on 2. So I've moved that over. Now, we know it's going to go, so we just know it looks like this, okay? So we've got that. That's my graph. We've got a trigger that it's got an x and a y intercept, yeah? So let's go find them. X-intercept is when? Y equals 0. Awesome. So we've got 0 equals 2 log 2x plus 3. All right? If you brought that 2 over to divide by 0, wouldn't it be 0? Yeah? So so I've got 0 equals log 2x plus 3. Now, do you remember, we could use that rule now where we flick it around. Remember I say, when you can say the base, 2 to the power of what it's equals 2x plus 3. Awesome. What's 2 to the power of 0?
1.
1 equals 2x plus 3. So bring the 3 over, it'd be 1 minus 3 equals 2x. So negative 2 over 2 equals x, which is? Okay, so you've got the x-intercept. Yeah? Okay? Alright? Because there was a bit of dilation in there, so yep. Okay. And now we'll do the y-intercept is when?
X equals 0.
Good. So you've got y equals 2 log 2 times 2 times 0 plus 3. So y equals 2 log 2, ooh, that looks bad, 1, 3, yeah? And you could even just change that to go log 2, 3 squared. Yeah? So log equals log 2, 9 or whatever. And you can just pop that in there. Don't have to convert that to a number. Just say 0 log 2, 9, whatever. Okay? That can be the number. Alright. Oh wait, so let's go. Domain for this guy. You've got it now. What can it be for x? Everything but, wasn't it -3 on 2? Comma, infinity. And what's the range? Real field. Good work. That would make sense. See how that flicked? So before, when we were doing exponentials, the range was set like restricted, and the domain was the real field. Remember when you find the inverse of something? Remember you flip their range and domain. So remember how I was telling you? Well, the log graph looks like that, and the that was the other way around. So they are an inverse of each other, so that means their range and domains would be the opposites. All right. Okay, cool. That's it.